Yep, welcome back. All right, we're going to look at the limit of sine x over x as x goes to 0. So previously we saw that this limit was 1, but we saw it in a way where we either made a table or we looked at the graph. So really they just kind of suggested the limit was 1. We couldn't figure out a direct way, though, to show that the limit is 1. So in other words, if I was to directly substitute here, I'd get sine of 0 over 0, right? And we all know that 0 over 0 in limit world is an indeterminate form. So what could we do here? It turns out that the squeeze theorem is going to be something that we want to try and do. However, we got to kind of get there first. So how do you do the squeeze theorem, right? We talked about in the squeeze theorem, the first thing you want to start with is a true inequality. So in order to get this true inequality for this particular problem, I'm going to look at the unit circle. So you can see I sketched the unit circle here, and then I drew a point outside the unit circle such that if I extended this line, it's actually tangent to the unit circle. And I'm interested in some areas here. So for example, I'm going to look at the area of that blue triangle right there. We'll call that the area of the big triangle. I'm also going to want to look at the area of that orange sector. So think of that as like a pizza slice, the area of that guy right there. And I'm also going to want to look at the area of the black triangle, which is going to be right there. So we'll call that the area of the small triangle. So we have the small triangle, we have the big triangle, and then we have the sector. And we're interested in seeing what's going on with those guys. All right, so where do we go from here? So let's go ahead and get to it. It's going to seem a little bananas, but let's do it. All right, so here we go. You ready? Let's look at the area of the small triangle first. So the area of this triangle right here. How could I represent the area of that? Well, the area of a triangle is going to be a half base times height, right? We know that. So the area of, say, we'll say the black triangle is 1/2 base times height. So what would the base of this triangle be? Well, this is the unit circle. So if this is the unit circle, this right here, the base of that triangle, that's just going to be 1. So that's pretty easy. And then now what's the height going to be? Well, this would be the height of that triangle. Now, what is that? Well, this is where it gets fun. Here is a point on the unit circle, right? So if I was to kind of drag this point around, that height of that inside triangle is always going to be a point on the unit circle, right? So I'll sketch it right back there. So the point on the unit circle, we should know from prior classes, you can represent any point, right, as cosine of theta comma sine theta. So in other words, the x values on the unit circle are cosine theta values, and the y values are sine theta values. Now, what is theta? Theta is this angle here. So depending on what theta is will depend on what the coordinates of this point are. All right, but it can be represented as cosine theta comma sine theta. Right? Equation of the circle: cosine squared theta plus sine squared theta equals 1. It's the unit circle centered at the origin. So now, how does that help me about the height? Well, think about this, right? The way you get to this point is you're going to go over some distance, where in this case that would be cosine theta, and then you're going to go up some distance. So then that would be sine theta. So the height of this triangle is going to be sine theta. So then I can just kind of spruce-reduce this up here. And so the area of that small triangle is just going to be 1/2 sine theta. All right? Not too bad. All right, so now let's look at the area of the pizza slice. All right, so the area of the sector. So the area of, all right, sector. Now, maybe you do, maybe you don't. The formula for the area of a sector turns out it's 1/2 r squared theta. All right, and I'll take a couple of seconds to kind of show you where you can get this if you didn't know. So maybe I'll do it down over here. If you have a circle, and I kind of take a chunk out of that circle, right? A little sector, a pizza slice, and I look at this arc here. So the arc of the crust, so to speak, we could say, all right, that's going to be theta. So, all right, theta, that's just the length of this arc related to the distance all the way around. Well, that would be 2 pi. It turns out that that is proportional to the area of this sector, call it A of S, right, as compared to the area of the whole circle, pi r squared. And if I was to cross multiply and simplify, I'm going to get here that the area of the sector is going to be 1/2 r squared theta, where theta is in radians, all right? And you can kind of do that on your own if you want. So now coming back over here, that means I would get 1/2 1 squared, because the radius is 1, theta. So in other words, 1/2 theta. So that is the area of my pizza slice. All right, rocking and rolling. Let's now go to the area of the large triangle. So the area of the big triangle. Well, again, area of a triangle, 1/2 base times height. So it's going to be 1/2 base. Well, the base of this triangle right here, right? This is the triangle I'm talking about. That's still going to be 1, right? This is the unit circle. That length is 1. The height now, a little bit more tricky. It actually turns out that this point, this distance right here, can be represented as tangent theta. So the height would be tangent theta. Now that's a little weird for people. So what I can do here for you is I can kind of draw this triangle out right here, label this theta, label this 1, and say, all right, I don't know what this is, so I can make up some variable here. I'll just do, I don't know, big M. I don't know what that is. So now you learned back in the day something called right triangle trigonometry, right? SOHCAHTOA. So tangent is equal to opposite over adjacent. So the tangent of this angle, since it's in a right triangle, is the opposite M over adjacent, which is 1. Solve this for M, right? Think about what you're going to get. You're going to get M is tan theta. So that's a little bit bananas, but that actually says that because this is 1, this length is actually just the tangent of that angle. All right, so we get 1/2 tan theta there. And now, why did I go through all of this? Remember, we're trying to use the squeeze theorem here. In order to do that, I want to start with the true inequality. The way I'm going to get my inequality for this problem is by the areas. I can say that the area of the black triangle, that's this in here, that's going to be less than or equal to the area of the sector, that's the orange pizza slice, which is less than or equal to the area of the big triangle, which is the blue triangle. So I can say 1/2 sine theta less than or equal to 1/2 theta less than or equal to 1/2 tangent of theta. Now, the or equal to might be driving you a little nuts, but if you think about it, if I drag this point here, right, look at what happens as I drag this point closer and closer and closer to the point 1, 0, right? Those areas kind of converge on each other. They get closer and closer. In fact, eventually they're all 0. So eventually they're all equal to 0. So that's why we say the or equal to, because if theta is 0 here, all of these guys are equal. So that's why I can put that or equal to in there. And so now, all right, what's the story? Remember, the goal of what we're doing here is to show that the limit of, in this case, since our variable is theta, the limit of sine theta over theta as theta goes to 0, we want to show that that is equal to 1, right? So I started with my true inequality, but remember now the second step that we talked about was you now have to get the function you're trying to get the limit of in the middle, squeezed in the middle. And half theta doesn't look anything like this. So, all right, let's go get them. So let's manipulate. The first thing I would do should be fairly clear is clean this up, multiply everyone by 2. So if I multiply everyone by 2, I get sine of theta equal less than or equal to theta less than or equal to tangent of theta, right? So you're like, okay, pretty cool. But there's a quotient here. So you're like, all right, well, why don't I just divide everyone by sine theta? So if I divide this by sine theta, I get 1. If I divide this by sine theta, I get theta divided by sine theta. And if I divide this by sine theta, I get tangent theta over sine theta. So now what do I do with this? Well, I'm going to focus my efforts right over here, and I'm going to simplify that. All right, I'm going to see if I can squeeze that simplification in over here. So tangent of theta over sine theta, I can write that. Tangent, remember, is sine theta over cosine theta. So now I can write all of this over cosine theta, but we learned that dividing by something in middle school, right, is equivalent to multiplying by 1 over. So by multiplying by the reciprocal. So that would allow me to cross out these tangent or sine, these sine thetas and just get this. So now I can come back over here and say, all right, 1 less than or equal to theta over sine theta less than or equal to 1 over cosine theta. And now you're like, wow, that thing in the middle, that's awfully close to this. The only difference is that it's flipped. So you're like, all right, not a big deal. I'm going to go ahead and just flip everyone. And just for note flow, I'm going to put this 1 over 1 and show you that now I'm going to flip it. So now when I flip it, it's going to be the red one over the black one, still 1. And then when I flip this, this becomes sine theta over theta. When I flip this becomes cosine theta. Now, here's the deal. If you're flipping sides in an inequality, you also have to flip the inequality symbol. You have to do that, right? So here to here, see how it's flipped, less than or equal to, greater than or equal to. Now, that should kind of make sense. Again, maybe I'll come over here to show you something. I could say like, hey, a half is less than 3. You'd all agree with that, right? But if I flip both sides, if I take the reciprocal of both sides, the reciprocal of a half is 2. The reciprocal of 3 is going to be 1 over 3. Well, now this doesn't hold true anymore. 2 is not less than a third, but 2 is greater than a third. And that'll always happen. And it's just the idea that, divide by a big number, you get a small number, vice versa. All right, so that's going on. So now I have, believe it or not, the function that I want sandwiched in the middle, albeit a crazy way to go about doing it. It is now right here. So now I can take the limit of 1 as theta goes to 0, greater than or equal to the limit of sine theta over theta as theta goes to 0, greater than or equal to the limit of cosine theta as theta goes to 0. All right. So now if the squeeze theorem is going to work, hopefully those outside limits are equal. So in other words, take a look at this here. What is the limit of 1 as theta goes to 0? Well, good news is it's 1. What's the limit of cosine theta as theta goes to 0? Directly substitute cosine of 0. That's 1. That's fantastic news. So now watch what we write here. So then we write that 1 is greater than or equal to the limit of sine theta over theta as theta goes to 0, which is greater than or equal to 1. So in other words, if we're saying that this limit, right, read it from the center out, is less than or equal to 1 and at the same time greater than or equal to 1, well, then therefore this limit must equal 1. And that's us showing the limit of sine x over x as x goes to 0 is 1. Now, you're like, wait a minute, you didn't say x, you said theta. That this variable is kind of like negligible, right? I could put any variable in here I want. So this directly implies that the limit of sine x over x as x goes to 0 is also 1. It could be sine y over y, sine g over g, sine box over box as box goes to 0, right? It's still going to be 1. You can actually replace this x with any sort of function. And if you drive that function to 0, then the limit of this quotient is going to be 1. All right? So pretty neat way to derive that the limit of sine x over x as x goes to 0 is 1. And we did it using the squeeze theorem. There's a little bit of magic going on here with the or equal to for all the mathy folk out there. But for the purposes of this video, this is pretty sufficient. All right, be good.